Okay, we're ready?
Yeah, we're
Yeah, we're
ready.
ready, bro.
Okay. Well, welcome to today's workshop, SolidWorks Simulation or FEA Part 2. Um,
Woo!
we will go over today the rest of the parts that we didn't go over last time. A review of last time, which is considered the Part 1. We only reviewed the external forces of just regular force and torque since they were the most common ones. Um, we will go like a little review with that before we start the part two. But for part two or today's agenda, we will go over the rest of the external forces that we didn't go over last time. The reason I split it up into those two categories was that these four that we're gonna go over today have one thing in common is that they all use a coordinate system, and you have to have a dedicated coordinate system in your simulation page compared to force and torque, which didn't really need a coordinate system. So the first one we would go over would be pressure. Um, of course, pressure works the same way as a force, but the only difference between a force and a pressure here is that the pressure is used in a way that simulates the behavior of fluids or gases either inside of a tank, which is fully sealed, or a tank that's open to the air, such as water pressure. And the only difference between uh, force and pressure here is that pressure could be expressed in functions. And since if you haven't taken fluids describes how the behavior of a water inside of a tank works. And the deeper you go inside of a fluid, the more pressure you experience. So that means more pressure into a wall. And the way pressure in simulations works is that you would be able to express that in a way of in a function, like in a function form, because in fluids, it's more like a linear, starting from zero all the way to its maximum pressure all the way at the depth, and that's how we would use it in simulations. And then the next one would be gravity, but I couldn't find a good illustration of gravity, so I will show you personally in the simulations. Um, but the next one after that would be centrifugal force or load. If you haven't taken dynamics, centrifugal force is a force that's being caused by angular velocity, something that is rotating within an axis. Um, the way that could be described is through this picture right here. Um, the person right here is spinning the ball within the axis, which is himself, and the centrifugal force is the force being caused by the rope and the ball, which I'm sure a lot of you could visualize how that works. You're spinning around, the string is being stretched out, right? That would be considered the centrifugal force. That could be applied to mechanical parts that are rotating really fast, and the same properties are applied to that, even though you can't really see it personally because it's usually metal or really hard materials, but that centrifugal force is usually there. So we would go over that today. And the last one that would be go we would go over today would be bearing loads. Of course, it's another rotation application here, but the only difference here is that it's focusing on the the forces being caused by the belts, because when you apply a belt to a rotating object, you try to like extend it as much as possible so there's no slippage, and you want friction forces to do most of the work. So when the belt is rotating, it wants to pull whatever it's rotating towards it. In this case, in this diagram, it shows FT and FS trying to pull this rotating object towards itself, and then the FB is the force, the reaction force preventing those forces from pulling it. So it's a static force canceling all everything out, and that force is being caused by the bearing. So and that's how a bearing load would work. So and those are the pieces, or those are the forces we would go over today. So the first one we would go over today would be the pressure one, and I will show you how to do the pressure gradient. Oh, seems that my thing got deleted. Um, well, we can make a new one real quick. We would, since I don't have that, we would go over that as a little review for right now. We would make a tank, which is the most common application. Any size is fine for now. All right, not wrong one. Okay. Okay, now we have our tank here. Okay. Now we would, since we have our tank, we would go to simulations. A little quick review of from last time is if you don't have it, uh, if you don't have the simulation tab on you and you barely opened up your SolidWorks, the way you can check if you have it is by going to the little gearbox and click on add-ins. And then right here you would have all the features that come with this application. Simulations would be right here, this colorful one. You would just check both boxes. If it's already checked, then it's already applied to it. But if not, you would just click both and click OK. And the way you would have it here is just right click anywhere in this box and then make sure it's checked. And then it would pop out right here. Okay. Okay. So you would click on the simulation tab, click on new study, static. Okay. So you would see the same menu as last time, but of course we would go over these: pressure, gravity, centrifugal, and bearing. Temperature is something else which doesn't include these. These two were on their own, but these four all include the coordinate system. So we will start off with the first part, which is defining our material. Right click on the on this tab, or you can just click right here, and you would have all these different materials. Usually for a tank, let's say a fish tank, right? It would usually be made out of plastic or glass. So we would go with any type of plastic here. Let's go with this one. Apply, and then close. Right? We're not worrying about connections as of now. The next part would be fixtures. You would always have a fixture somewhere, or else your simulation will not run. So of course, either right click or click up here. We'll go with fixed geometry. For a tank, you usually have it under here. It would be like on a table or some beams. You can simulate beam structure here if you want, but for simplicity, we would go with just a table. Okay. And for the external load, we would go with pressure. Of course, you could use pressure just the same way as a force. Just click anywhere, right? But what we're interested in is the way it behaves with the fluid. To do that, you would have to create a non-uniform distribution. As you can see, it does ask for a coordinate system, which we don't have. So we would need to put one. So to put one, you would go to features, you would go to reference geometry. If you want to put a coordinate system in a certain direction, because the placement of the coordinate system matters. So if you put a coordinate system like all the way down here, it would affect your distribution gradient. So if you want to put, you would have to put your coordinate system at the top of your fluid. So in this case, it would be all the way at the top, right here in this face. So in order to put your coordinate system where you want it, you would have to put a point first. So where would you want your point to be? Oh, all the way up here, center of that. That's that's already good. Okay, and then you would add your coordinate system. You would have to define your directions. For this case, since our fluid is going downwards, we need our y to be pointing downwards. In order to make it pointed downwards, you would just click any face that's below your coordinate system. In this case, it's down here, as you can see. Oh, no way. Yeah. As you can see, well, you got to do x first. So x would be this one, and then your y would be this one. There you go. You can see the y is now down, pointing downwards. That's what we need for a pressure gradient. So now you would go back to your simulations. Now you would apply pressure once again. Non-distributed load. It already picked your coordinate system for you. That's fine. When it comes to putting non-distributed loads, you have multiple coordinate systems. You have your regular Cartesian, you have cylindrical, and you have polars. Spherical. My bad. For the simplicity of this, and you already have your x and y coordinates, we would just use Cartesian. We could probably talk about cylindrical and spherical at a later date, but for now, we would just go over Cartesians. Of course, you could change your your unit system. Um, I usually go with meters, but this is where you would change your gradient with edit the equation. You are given this equation that would help you define what what is going on here. For a normal tank, you normally don't have an x direction and you don't have a z direction. You only have a pressure gradient going downwards. But if you were to put it, if you want to have like different pressure gradients in different directions, you would put a number here. Right now, since everything is one, like it has no number in front of here, no number in front of here or here, everything would be evenly distributed. So there's no point of using this non-distributed load. So in order to change that, to show a a pressure situation, there is no x, there is no z, there's only y. So in order to get rid of x and z, you would have to put a 0 and an asterisk in front of it. And same thing for the z. And for the y, since you want that one to be active, of course you can put functions if you want. Uh, but for simplicity, for the y, you want it to be active, so you would put a 1 and then an asterisk. You would click this confirm, and now you have your equation that would simulate this exact scenario. As you can see, y, you want the function to be this linear one. Of course, if you wanted an x and z direction, it would do the same thing, but in the respective coordinates. So of course, you would put as much pressure as you want. Let's say 80 psi, and then you would go back here, which is what faces do you want this pressure to be applied to. So of course, it would be in the bottom, here, 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 and here. Okay, that's where all your pressure would be. Okay. Some reason it's not really applying what I told it to do. Maybe it's too high of a pressure, so yeah, it's not applying what I want it to apply. Yeah. Well, it just shows that this the position of the coordinate system is really important. Um, well, let's change that and see what happens. Let's erase this and this, and now let's add a new coordinate system. X. No, that's not what I wanted. I want it here. And then the Y would be down here. And of course the Z here. Now to see how this works out. Just to show the different positioning of a coordinate system. Not uniform, of course, it's already selected. Same thing. One there. And a 0 here. Go. Okay. To meters. Now let's make it 20 psi. Select our faces. It still doesn't want to show. Well, technically it will show the distribution right here. It would show these are smaller arrows and they would keep getting bigger and bigger. But for some reason it doesn't want to show. Yeah. Well, that's the general idea. You would put in your coordinate system and you would tell the program what equation you want it to be. And it would show it here. Oh, let's see, there you go. I don't know why I didn't show it normally, like as an example, as a preview. It would I don't know why I didn't show it as a preview, but this is how it's supposed to come out. As you can see, small arrows, and then it keeps getting bigger and bigger and bigger, right? And at the bottom, of course, it's all distributed because that's where the maximum pressure is equal, right? It's only applying pressure to the walls at a function, right? As seen here, everything here is even, and right here is the maximum pressure, as you can see, a line or a slope, and you could pretty much simulate it here, right? And then once all that, you apply your pressure, you would be able to run a simulation now. And there you go. This is the simulation of water inside of a tank with a certain amount of pressure. Well, it couldn't be water because we picked a random pressure gradient, so it could be any. You would have to look that up, what the pressure of water would be. Um, but in this case, let's just say it's water, for simplicity. Um, this is the stress it would cause to a open air tank, of course. Um, this is an open air tank. What if we wanted to do it to a closed system, like a gas tank or something? Um, well, we would go over that right now. That's our next example. Now here I have a regular container. You could probably design a soda can and simulate soda inside of a can, see what would happen, how an aluminum can would work, uh, a gas tank with propane, something like that, or maybe some tubes transporting natural gas. You could simulate uh, any type of closed system. So of course you go with new study, same thing, apply a material. Since we're talking about, let's say for this case, we're talking about a gas tank or a pipe or something. So we wouldn't use plastic, right? We would use some kind of metal like aluminum or steel. Let's go with just any of the steel, anyone in the steel category. Of course, no connections unless you can combine all of them. But let's see, fixtures. Let's say this gas tank is being held by the top and the bottom. So you would have a fixture there and a fixture here. So it's like being held sideways, right? Okay. Now external loads, of course, you want a pressure. But since it's closed, you won't normally have a non-distributed pressure. So in this case, it would be easier than a tank full of water. So you would just use the normal pressure valve because everything's gonna be distributed. So you're probably wondering, how do I put the pressure inside? So you would want to split open this piece. So you would click here in selected view. Of course, you would pick what which which plane or which face do you want to cut open, right? So I want to cut open right through the middle. So I would need a plane that would cut right through the middle. This one cuts right through the middle, right? So click on right here, selected view, and I click. I don't know why it doesn't do that. There you go. So now you see the middle. Now you see the inside, but it still simulates the whole thing. So an external load, you put pressure. Now you're able to put pressure on the inside. As you can see, it even simulates the other half. See? But you want pressure on everything, right? So you have to click here, here, and then the top as well. And there you go. See? It simulates even the second half. Of course, you would put a pressure. You would have to look up how much pressure a propane or carbonated drink would apply. But for this case, let's go with 30 psi. Right? And then you would just run the simulation. And you can see most of the pressure is coming from the sides. Which, if you take in strength of materials or machine design, you would be able to tell that this makes mathematical sense. So it's a good starting point for any simulation. Okay. So the next one we would go over would be gravity. Okay. Uh, the way I didn't show gravity this time, well, I didn't show it in the PowerPoints was because I couldn't find a really good picture to describe how this would really work. Imagine the way gravity works in simulations is how the material affects itself under gravity, like collapsing beams and stuff like that. Imagine a beam being supported by two supports, but the beam is really long. Um, of course, that beam is gonna bend under gravity, and that's what simulations here is trying to show you. and I couldn't find a good picture describing that, so that's why I didn't put it in the PowerPoints. But I'm gonna show it here. Um, so of course, it already has a steel applied to it. Let's see. Let's pick really, you know, even if we pick the soft material, it'll still have enough strength to support itself. So we're just gonna stay with steel. So of course, pick a fixture. For this, we would just pick the bottom, because imagine the tank is just being put on top of a table or the floor, right? And then external loads, we would pick gravity. Of course, the center of gravity of this tank would be put here. The gravity will always be normal to your fixture, right? Since our fixture was down here, assuming that the table is right here, of course, gravity is gonna point towards that. Um, the good thing about this is that SolidWorks doesn't have a concrete or like a set gravity like 9.8. It lets you change it to any type of gravity. So let's say you want to simulate gravity on a different planet that has higher gravity or a planet that has lower gravity. So you would be able to change it here. Uh, of course, it doesn't allow you to change the unit system because it uses the unit system you have previously set since the beginning. So you would click OK, and you would just run the simulation. As you can see, super exaggerated. You would be able to see how it really implodes on itself, especially towards the middle. Since in the middle, there's no structure in the inside that helps the middle part stand up. So of course, that's where most of the imploding happens. Right. Same thing here. Since it's like really curved, most of the gravity is telling this material to like collapse here, right? But since this material is much stronger than gravity itself, uh, than the force of gravity, it's it's in the green, so it's not really gonna collapse due to gravity. It's probably gonna collapse due to something else. Um, that's how you pretty much just do gravity simulations here. So the next one would be centrifugal centrifugal force. For that one, a basic I have a basic wheel, basic circle. Oh, for this one, of course, I already have my coordinate system. Um, so that doesn't really have to apply. For this one, when you apply your coordinate system, uh, your y has to be in the direction of what the belt is being pulled at. So going back to this picture right here, since the force is being pulled that way right here, your coordinate system would be have a y pointing that way as well. So if you want to change that, of course you can. So since I already put the coordinate system, uh, of course, putting a point and then putting the coordinate system would allow me to put my coordinate system wherever I desire. In this case, I put it here. You could either put it over here as well, or you can even put it in the middle if you have anything that would help you put a dot in there. So run a new study. Of course, let's apply our material. Let's see, what's a material that uh, stretches out a lot when it's spinning really fast. Of course, steel wouldn't you wouldn't be able to see it with steel. So maybe with some rubber. Okay. It seems that the information for rubber is not available. You would have to put that manually. So let's look for a value. a rubber that has values. So SolidWorks doesn't have any rubber that has a complete values. So it seems that we can't use that. What's another material that, let's go with silicon. Okay. Fixtures. Your fixture here, of course, has to be inside because that's where it's being held onto, right? Like let's say you put a tube in there and then you start spinning it, of course the fixture would be inside there, or else this won't be able to spin. Next thing would be the external load, centrifugal. You would want, it's telling you to select the face that is gonna be applying, is gonna experience most of the torque. In this case, it would be this one, because that's where all the that's the face that's being stretched out. Um, it's gonna ask you what's the angular velocity that it's spinning at, and it's gonna ask you what's the acceleration of that velocity. You could either have it zero for a constant velocity, or you could put in a number between negative infinity and infinity to change that velocity. If you have a negative acceleration, it's gonna have your angular velocity and it's gonna start going down and down. If you have a positive acceleration, it's gonna start from your maximum and it's gonna start increasing. So let's say with the angular velocity of maybe 90 hertz. Of course, you can change the system here. G's. Let's say with an acceleration of maybe 4 hertz per second. As you can see, it gives you the direction. Of course, you can change the direction, the rotation, by just clicking the reverse. You don't have to put negatives here if you want. If you want to slow down, this orientation tells you. The big one tells you the angular velocity, telling you it's spinning this way, and if the acceleration is spinning the other way, it means it's slowing down. If you want it to spin the other way and speed up alongside the velocity, then of course you want to go the same direction. Oh, my bad. The big one, uh, yeah, the big one is the acceleration, and the small one is the velocity. So okay, and then you would run this study. As you can see, as shown in the picture, it stretches out. Another example I can give you for this one is imagine a pizza maker, right? As you can see in those movies and the TV, they have a bunch of dough and they're just spinning it in midair, and the central axis of rotation is in their fingers, which is in the middle of the dough, and the more they spin it, the more it stretches out. That's what centrifugal force is. Um, of course, in machines using like these high materials, you won't really see it, but it's still there. And SolidWorks allows you to apply that option here as well. A super exaggerated force, as you can see, this is the original shape, and it's exaggerated a lot of stretch. Most of the stretch or the stresses is where the the um, the fixtures are, because that's where it's really condensed. And of course, in order to stretch the outside, the inside has to be stretched more. So that's where most of the forces are. You will learn how to do this manually in a different class, like machine design. I don't know about other classes, but you would be able to like visually confirm this just based off of your experience in manual calculations. Uh, this is the original shape, of course. Um, that is centrifugal force. Of course, this could be applied to a gear, um, uh, a belt wheel, a bearing, of course. But most commonly, it's used for uh, belts, like things that spin. Technically, it's just pretty much that. Anything that spins. And then the last one for today is the bearing load, which will show the belt deformation. First one, I have a regular container, right? A regular machine part that would be applied to, that would be inside of a machine, and then the circle would be where your bearing would be, right? So we would put, for this one, of course we need a coordinate system. So you would put your own coordinate system. So a point, I want it here. Of course, you could decide where to put your point. You can put it at the center of an arc, at the center of the whole face, or an intersection. Um, since the circle here is in the middle of the face, of course, the arc and the center of the face would be the same. See? But for this case, usually when you're doing a bearing load, you would want your dot to be in the middle of the circle. So if your bearing position is not in the center of a face or anywhere, you would of course use the arc center to put your dot. And then you apply your coordinate system. Same thing. You would want to put your y position or any position, your x or your z, in the direction of whatever your belt is being pulled at. So same thing here, how we talked about your y coordinates being in that direction. Same thing here. So you would have your coordinate system, and you would want your y direction or your x direction to be in the direction of these forces. So in this case, I'm assuming a belt is being pulled upwards, so I want this x or this y to be in that direction. So x, y up here, and then z. It usually doesn't ask for a z, so you can pretty much just not put anything there. But if you want a z, then of course you would put a z. And then click OK. And then you run a simulation. Static. Of course, apply a material. Most commonly used in industry is, of course, steel. Stainless steel. Let's go with that. Fixtures. Let's say the piece is inside. Say it's bolted down from down here. Like let's say there's bolts holding this down. And then for external load, bearing load. As you can see, you would want your face to be the inside of where the bearing is supposed to be. So in this case, it's right here. As you can see, it's going in the x direction, but we wanted to go in the y direction. When it gives you the option to select your bearing load here, it gives you x and y. So of course you would click on the y, and it will change it. Of course, your coordinate system is going to be the one you define. How much is the belt being pulled at? In this case, it would be a preload. Um, Imagine a bike, right? And it's chain. When you change out the chain, right, you put it on, and then you would pull the wheel back as much as possible to increase the tension so it doesn't slip off. Um, that's what's happening here. So that preload is this pounds foot that you're applying. So the belt would be like on a preload of 20 pounds foot. Of course, if you want the other direction, you just click on the other direction, right? And then you'll run the study. As you can see, it's to be expected that you're pulling the rod that's inside the bearing upwards with the belt, so it would cause a deformation like that. Of course, you could also do it in the X direction. You could do it in the Y direction as well, and even you kind of do it in the Z direction because there's no wall in between, so it only gives you two at a time. And as you can see, most of the stress is right here because that's the center of where the pole or the tube that's being pulled is at. Um, and this is the last one of the forces that we didn't go over last time. We went over pressure, gravity, centrifugal, and bearing. Uh, we could probably go over temperature at a different day, but for this club or this organization doesn't really handle with extreme temperatures, so I feel that wouldn't be necessary for this case. But um, you could try it out if you want. And the one thing when it comes to simulations is that one cannot be taught everything because there's some things that might be missed. The way to learn this is by going in yourself and doing all these examples for yourself, because you might find some tricks that might help you but not benefit others. Um, what's good about SolidWorks is that there's different ways to do things. Like, for example, pressure and force could technically be used as the same thing. So you might find a way to completely ignore force and just use pressure. That's up to you. Um, I highly encourage that you do simulations on your own. Look up. You could probably do simulations on the T slot that we're working on. Um, you could probably use all of these if you want, but it's really highly encouraged that you work on it on yourself when you have time, free time. You're probably bored at home. You could probably do some simulations, and that would be the end of part 2 of FEA. Of course, I haven't gone over these other connections. They could probably go over. We could probably go over them at a later date as well. We could probably include temperature with it, and we'll see what happens. Uh, Thank you for coming to part 2 of FEA.
That was